In this video, we are going to talk about induction, and this is one of my favorite topics along with infinities. And the reason why I like induction so much is because when I first saw it, I thought it was really suspect, and I didn't really understand what was going on. But then I had a professor explain it to me, and all of a sudden it seemed quite brilliant. Hopefully, by the end of this video, you'll have some affection for the subject as well. This is the overview slide that has all the main ideas of induction. The first thing to know is that induction relies on the well-ordered principle of the natural numbers. So if S is a non-empty subset of the natural numbers, then there exists an element M in S such that M is less than or equal for all K in S. In other words, there's a smallest element. The ability to find a smallest element in a set would not be able to be done on an open interval of the real numbers, such as the open interval 0, 1. Also, it wouldn't be able to be done on a set of complex numbers, but while we can compare magnitudes of complex numbers, we really don't have a way of ordering them. This fact is important to know because you need to know what the limits of induction are, although you can apply induction in sometimes very clever ways. And I will give you one example of something very clever. The theorem, that is the principle of mathematical induction, says if P of n is a statement that is either true or false for each little n in the natural numbers, if the base case is true, P of 1 is true, and for each k in the natural numbers, the inductive hypothesis, which is if P of k is true, then P of k plus 1 is true, then we can conclude that P of n is true for all n in the natural numbers. When I do an inductive proof, these are the 3 steps that I follow. First, I show that the base case is true. In other words, I show that for n equals 1, this is true. Again, here, this is this part of the theorem. Next, I have my inductive hypothesis step. I assume that the statement is true for n equals k. In other words, I assume P of k is true. This is this part of the mathematical induction principle. Then last, I show it must be true for n equals k plus 1. That is, if P of k is true, necessarily P of k plus 1 is true. So also notice, I use P of k to show that P of k plus 1 is true. This is this part of the hypothesis. And then last, I can make a conclusion that P of n is true for all n. That's my conclusion for my principle of mathematical induction. And if you're already feeling suspicious of this, we will get to that. But let's continue with an example just so that we can have the mechanics first. Next, I am going to do an example. Now, if you've already have misgivings about the principle of mathematical induction, I will tell you that after we've done the example, I'll go through that and tell you what made it suspicious or suspect to me, and I'll tell you the story that kind of helped me see that it was actually just really brilliant. But first, just so that we have the mechanics of what's going on, we will do this example, which is to prove that 1 plus 2 plus 3 up to n is equal to 1/2 n times n plus 1 for every natural number. Doing my proof by induction, I do the first step, which is the base case for n equals 1. So I show that P of 1 is going to be equal to 1/2 times 1 and then 1 plus 1. And you can see that this side of the equation is also equal to 1. So my base case holds. My next step is to assume for n equals k. So in other words, my inductive hypothesis, so I abbreviate that IH, is to assume P of k is true. In other words, 1 plus 2 plus up to k for n equals k is equal to 1/2 k plus 1. So we're going to assume this is true. And I know this looks really sketchy because this is exactly what we're trying to prove, except that instead of n, we just substituted a k. But we'll get back to an explanation about that later. But for now, we're just going to go through the mechanics. And my last step is to show that P of n is true for n equals k plus 1. And essentially, I'm going to use my inductive hypothesis, P of k, to show that it must mean that P of k plus 1 is true. So I'm going to show P of k plus 1 is true. So I start by writing out my P of n in terms of P of k. And one thing I'm sure to do is when I write out my terms, 1 through k plus 1, I show my kth term. Then on this side, I have my 1/2 and my k. So here's my 1/2 and my k plus 1, right? Because n is k plus 1 at this point. And then if n is k plus 1, then I have a k plus 1 term here. And here, this is why it is important I show my kth term, because now I can use my inductive hypothesis. By my inductive hypothesis, my first k terms is going to be equal to 1/2 k plus 1. So I'm going to substitute this using my inductive hypothesis for my first k terms, and then I have my plus k plus 1. The next part is I'm going to do my algebra on the left-hand side. I'm just going to bring down my right-hand side because I want to show that this left-hand side will equal this right-hand side. So you can follow through the algebra and you'll see eventually I get the left-hand side equal to the right-hand side, which means that k plus 1, I have shown that k plus 1 is true by using my inductive hypothesis. And this is a critical step. And it's critical on this third step when you show n equals k plus 1 is true, you must use your inductive hypothesis. Otherwise, you're not doing an inductive proof. And then finally, at the very end, I can make my conclusion that P of n is true for all n in the natural numbers. And as I mentioned, the sketchy part is right here. You assume exactly what it is you want to prove. So this is how this was explained to me. So you think of induction as a ladder. So there's this ladder, and of course it's a mathematical ladder, so you can't be assured that you can climb onto it, except that you are told that there's a base case, there's a rung sufficiently low or easy to climb onto where you can step onto the ladder. So that is your base case. There is a low enough rung that you can get started on the ladder. Then once you're on the ladder, once you're actually on the kth rung, you are told that you can reach the k plus 1 rung. So if you assume you're on the kth rung, you can reach the k plus 1 rung. And then by this, because you have a place to start and you can keep going up one rung at a time, you know that you can reach all the rungs of the ladder by climbing up. So looking over our proof again, we have the base case, we have a place to get started on the ladder, then we assume once we're on the kth rung, we can go up one more rung to the k plus 1 rung. So since we have a place to start and we can keep going up, we can traverse the ladder, and then we know P of n is true for all n in the natural numbers. And I will remind you, it is important to have a base case, otherwise you can't even get started on the ladder. And then this is your inductive hypothesis. It's important you use the inductive hypothesis, otherwise you don't have this second condition here. And last, you want to make your conclusion in your proofs. Sometimes I'm lazy and I don't write that, but if you're in class, I would suggest you do that to make sure you get full credit for your work. As I had mentioned, induction is about the natural numbers, but there are ways you can use the induction in a very clever way. For example, I believe this is a Euclid proof, to prove there are an infinite number of primes. And the first challenge of this is to formulate our P of n. And our P of n is going to be there are at least n primes. Now that we have our Pn, we can start our proof by induction. The base case is fairly straightforward. So we want to show P1. In other words, there is at least one prime. So we can pull out the number 2 and say, look, there's a prime. Second, we do our inductive hypothesis. We assume this is true for n equals k. So we're going to assume pk, that is, there are at least k primes. And we're going to call them p1, p2, up to pk, p sub k. And just a note, these are k primes. They're not the first k primes. So in other words, this may not be the number 2, 3, 5, 7. They're just random primes. So it could be 3, 11, 17. And the last step is to show the inductive hypothesis implies p sub k plus 1. This last step requires some cleverness, but we can consider our first k primes. If we multiply them all together and then add 1, this sum here, either the sum is going to be a new prime, or if it is not, if it's a composite number, then we know that this composite number has a prime factorization where p1, p2, up to pk, none of them are in the prime factorization. In other words, p sub k, this sum is going to have a prime factorization with a new prime. So I'll give you an example. Say we started with P1 is equal to 2, and then by our formula, we're going to multiply all of our P's together, which is just 2, and then we're going to add 1. So that'll give us 3. So that's a new prime. So P3, to generate a new prime, we're going to multiply all of our primes together, 2 times 3, and then we're going to add 1, and we get 7. That's another new prime. P4, we get 43, so that's another new prime. So this kind of illustrates this first part where the sum of the factors multiplied together plus 1 is a new prime. But what about this second possibility? Well, instead of continuing with this, because I'm going to have to start multiplying big numbers, which I don't like to do, I assume that P1 was 3 and maybe P2 is 7. And then you can see my next P3 using this algorithm here would be 3 times 7 plus 1, which is 21, which is not prime, but it has a prime factorization, 2 times 11. And because of the way it's constructed, you know that 3 cannot divide 21 and 7 cannot divide 21. So you know it has to have a new prime, and it does, which is 11. And the point of this example wasn't so much that you learn how to generate primes, because you know how to do that, but to show you that there are very clever ways you can use induction. This next example is a more typical problem of what you might get in a class. So we're going to prove for all integers n greater than 3, 2 to the n is less than n factorial. We start with the base case. In this case, this is true for n greater than or equal to 3, so we're going to start with n equals 4. So we have 2 to the 4th is less than 4 factorial, and sure enough, 2 to the 4th is 16, which is less than 24, which is 4 factorial. Our second step, fairly straightforward again. We're going to assume for n equals k. So in other words, we're going to assume 2 to the k is less than k factorial if k is greater than 3. Our third step is to show for n equals k plus 1. So I'm going to plug in k plus 1 for n. So I get 2 to the k plus 1 is less than k plus 1 factorial. And the critical thing here is because I want to use my inductive hypothesis, I need to break this down so that I can use my inductive hypothesis. So 2 to the k plus 1 is equal to 2k times 2. And this k plus 1 factorial is equal to k factorial times k plus 1. Now I'm in a position to use my inductive hypothesis. By my inductive hypothesis, 2 to the k is less than k factorial by IH, inductive hypothesis. And since 2 is less than k plus 1 for k greater than 3, the product of these two will still be less than the product of these two because of the way this less than equals. And I can make my final conclusion that Pn, which is 2 to the n is less than n factorial, is true for all n in the natural numbers. Another good example is to prove 7 to the n minus 4 to the n is a multiple of 3 for all natural numbers. I have my base case where I show for n equals 1. I plug in 7 to the 1 minus 4 to the 1 is equal to 3 times h1, where h1 is equal to 1. In other words, h1 is just some integer, saying it's a multiple of 3. And then I'm going to assume, use my inductive hypothesis, assume for n equals k. So I'm going to assume 7 to the k minus 4k is equal to 3h, where h is an integer. In other words, this is a multiple of 3. And the third step, I'm going to show for n equals k plus 1, and I need to use my inductive hypothesis to show this. So I'm going to plug in my k plus 1 in for n. So I have 7 to the k plus 1 minus 4 to the k plus 1. And I want to show that's equal to 3 times some integer h3. And now, again, the trick is I want to be able to use my inductive hypothesis for k. So I'm going to separate out my k. So 7 to the k plus 1 is equal to 7 times 7k minus, and then 4 to the k plus 1 is equal to 4 to the k times 4. This requires a little bit of algebraic manipulation because I want to get this form, 7k minus 4k. So I can kind of force that 7k minus 4k. I can still multiply everything by 7, and that will be good for this term here, the 7 times 7k. But then I've just multiplied this by 7, so I'm going to have to offset that by adding another 7 times 4k, and then I'll also put in my term, my 4 minus 4k over here. So this looks really messy, But when I use my inductive hypothesis, I see that the 7k minus 4k is equal to some multiple of 3. So that's equal to 7 times 3 times h. So this makes this a multiple of 3. And then fortunately, because I have a 7 here and a minus 4 here, I have a 3, a factor of 3 here. So this, I can factor out my 3, and I see that this is going to be an integer and will be divisible by 3. And finally, I can make my conclusion. That covers the main ideas of this chapter. Next, we'll have some review problems. Here are 3 problems for you to try by way of review. You should pause the video, give them a try, and then come back and I'll have solutions for you. Here is the solution for the first problem, and you don't want to get so caught up in your algebra that you forget to use the inductive hypothesis, so this step is critical. Here is the solution for the second problem, and I know I said using the inductive hypothesis critical over here, and of course the base case is pretty critical. And this is the last solution. That's it for this video. Thank you for watching.